Well, good evening, everybody, and welcome. I know there are a few visitors tonight from the solar section, and you're especially welcome. That's great. Um, good to have you. Good to have you with us. A couple of points on housekeeping. One, half time tonight, this evening, I'm going to try breakout rooms. I don't know if anybody's ever tried that before, but Zoom will allocate us a room where we can just have an informal chat for a few minutes, probably about 10 minutes. So we'll see how that goes at half time. And the other point is, when we put a call out on the Google I/O site for training, there is a whole flurry of interest, and our inboxes get inundated with everybody's request saying, "Oh yes, I'm interested. I'd love to join." What you can do with the with Google Groups is to consolidate the messages so you get one email per day. If you go into the subscription and email delivery section, you can manage that. So if you do get irritated by loads of messages, you can eliminate that and bring it down to just one per day. Okay, at this point, I'm going to hand over to Paul Hyde, who's got something to say to us. Paul, the floor is yours.
Well, it's actually Carndine, but never mind, it's new. Right, and I have paid for it, so I guess the floor is mine. Right, good evening, everyone, and especially, again, for the those from the solar section. It's good to see people. Very quickly, so the idea is to have something along the lines of the annual general meeting that the Radio Astronomy Group used to hold. We had 4 or 5 meetings at Leicester or Northampton, which were very successful. We tended to get sort of 70 or 80 people, which is very high numbers. So that's gratifying. This year is a bit problematic. We're thinking of October. So plenty of time for planning, but the expectation is that we should be in a much better place in October than we are at the moment, but we can't guarantee it, and making arrangements that far ahead is probably problematic. So the feeling is that we should do it as a Zoom event, something like that. The exact format, we haven't decided yet, because it could be that there's a lot of interest for a sort of one-off annual event. And Zoom does have a limit of 100 people. So there's some discussion as to how we run that, whether we run it as a webinar or as a Zoom meeting plus YouTube overflow, but that's it. Anyway, the question is this: if we're going to do this, we need presentations. The format that we've used in the past, and which we hope to use again, is of 1 or 2 keynote speakers, so professional astronomers with an area that's related to radio astronomy, supported by papers and reports on what members of the group have been doing. I'm just a little concerned that with the success of what Paul Hearn has organized in terms of workshops and these Zoom events, whether, you know, we've got a supply of presentations or potential presentations for October. So I would very much like to hear from people who feel they have got or would have by October an offering for a one-day Zoom event on radio astronomy. To counter the disadvantage of it being a virtual event rather than the pleasantries of actually meeting people and whatever, there is always the possibility of being a little creative and maybe a presentation that is not purely based upon a PowerPoint slide deck or whatever. So videos, that sort of thing. I'll leave it to people's thoughts and imaginations. But in the first instance, could people let us know if they might have something that they could offer as a 30 to 40-minute presentation in October? And that's my bit.
Thanks, Paul. Excellent. My email address is sent out with this invitation. You can email me. I won't put Paul's email address in the chat here because of GDPR regulations, but I can send Paul's email address out on the list, and that would be perfectly acceptable. Shall I do that, Paul? Yes, with a reminder to everybody that to contribute at the October meeting would be just fantastic. There was one point of housekeeping that I forgot to say, and that is once you're registered with this group for the email link, then it's the same group that's used for all our events. I don't have the administrative wherewithal to create separate groups for each event. The next meeting is April the 23rd, geomagnetism, and that's with Reeve is joining us from Alaska. Again, I doubt if that would be possible if it wasn't for Zoom. So really looking forward to that talk. 2 training workshops that we've already spoken about. There's an introduction to Python for radio astronomers. Thank you very much, Rue. And then working with Spectrum Lab, which has some bearing on tonight's talk. That is it from me. So without further ado, I'd like to hand over to Mark Edwards. Mark, the floor is yours, or the screen is yours.
Except you've disabled it.
Oh, sorry. Share screen. Allow participants to share screen.
This always happens on Zoom. So.
Check. Have you got it now?
Oh yeah, I think so. Let's try that.
My mistake.
Oh, can you see that?
Yes, that's going to work.
Good. Right, hello to everyone. I was asked to talk about my observations using VLF, and I thought I would start with this wonderful picture of the atmosphere. And I always like to think of the atmosphere as a free particle detector. I mean, people spend lots of money building huge detectors for CERN and other accelerators, but we've got one the size of the Earth, which is free, so why not use it? And the poor old atmosphere, it's squashed between the Earth and space. So what happens is that you've got photons coming in, like extreme ultraviolet photons, which ionize part of the atmosphere, and you've got X-rays, which do the same, and also gamma rays. And when these come from the sun, we have the extreme ultraviolet is there all the time, that the sun's above the horizon. So during the day, the top part of the atmosphere is highly ionized from that source. Now, the other sources like X-rays and gamma rays, these are less frequent. They occur randomly all the time from outer space. But from the sun, we tend to only get the X-rays when we have a major flare on the surface. So the X-rays tend to depend on the sunspot cycle, whereas the extreme ultraviolet is there all the time. So we've got photons trying to bash the top of the ionosphere. And we've also got particles, charged particles from the solar wind and cosmic rays. And besides those charged particles, we also have dust in the form of meteors or fireballs, bolides, or larger objects collide with the top of the atmosphere, ionize it, and jiggle it about a bit as well. And so they're the ionizing sources. You probably can think of plenty more, which come from the from space onto the top of the atmosphere. But from below, we've got the lower atmosphere tends to wobble the ionosphere around a bit. So we've got things like weather fronts. Say we've got rising air off a weather front, or we've got the jet stream, turbulence in the jet stream can produce instabilities in the lower atmosphere, and they propagate up to the higher atmosphere and wobble the ionosphere around as well. We've also got effects where the wind, say, goes over a mountain range, creates turbulence, and that can propagate upwards. And surprisingly, we've got earthquakes, and you've got the sort of general shaking of the ground on an earthquake, but you also get things like tsunamis, which push the level of the sea up. And of course, the atmosphere sits on the sea as well. So that can propagate upwards. And we've got obviously storms, and the major ones here are lightning storms, which I read they can even create gamma rays from the lightning strikes. So all these effects are going on at the same time, and all the information about what produced these effects is stored in the ionosphere. And our main problem is trying to get this information back out. So we've got our nice free detector. So what we need now is a nice free way of reading out this information. And there are various ways of doing this. You can use different frequencies, like in an ionosonde, or you can use things like VHF, where people do a lot of meteor scatter. But the one I choose to use is VLF. And one of the main reasons is that if there's very strong ionization in the ionosphere, it tends to absorb any radio waves trying to go through it. And what happens with VLF is they just bounce off the bottom layer of the ionosphere, the D layer. And so when we get a major X-ray flare, it doesn't stop us from reading the information out. It actually makes it better. So how do we get our VLF transmitter? Well, the governments provide them for free, because they like to have submarines, paying submarines. And the thing about VLF, of course, is that it propagates into the conductive sea to a few tens of meters, which means the submarines don't have to surface in order to receive instructions. And they're all around Europe. So there's one in TFK in Iceland, there's a couple in the north of England, one in Germany, a couple in France, one down Sardinia, and one or two others scattered around, and one in North America. And all these transmitters, they're transmitting in the region from about 16.8 kilohertz up to 37.5 kilohertz. And they're so secret, these transmitters, that you can see them on Street View. So this is the one at Anthorn, just north of the Lake District. And The thing with these VLF transmitters is they use a vertical antenna, so they're vertically polarized, and all the other masts are to take the top hat. And the whole thing is enormous, 1 kilometer across. And the saying goes that Skelton, which is the one sort of by the Lake District, and tall mast in the middle and an array of other masts around, to just do this capacitive hat, to try and get the efficiency of these things up. And they transmit with about 0.5 kilowatt. And this is my receiving aerial. At great expense, it uses a loop of SCART cable. So if you've got all these cables you don't know what to do with, make a VLF aerial out of them. So the thing is that the transmitters are vertically polarized, so the magnetic field is horizontal. So a nice vertical loop will pick up this magnetic field. And you then have to point it in a particular direction. And it just so happens the wall of my shack points vaguely east-west. And that's probably the best way to point it, because of trying to get a good reception from the station in North America. You have to point the loop towards the polar diagram of the loop means that it's more sensitive if the loop is actually pointing in that direction. So pointing it east-west is, you know, probably about the best direction to have. And you'll see at the bottom, there's a VLF receiver. That's where I started off experimenting with, but I don't use it any longer. And one of the main problems is that it only works on one frequency. And you've got all these transmitters around Europe. So it's a shame not to use them all. And as we'll see, it's at a great advantage that you use as many as possible. And the other thing to do is when you've wired up your SCART cable loop, is to put some protection diodes on, because if you're interested in detecting lightning, it makes an excellent lightning detector, as you can see from this, from about, what's that, 4.5 years ago. So yeah, it has that use as well, observing at VLF. So that was my aerial, a lot smaller than the transmitting aerial. And this is my new receiver, which replaces my expensive VLF receiver. And all it is a PC. It's just a Zotac mini PC. But the best part of it is that the bandwidth of the microphone input is 48 kilohertz, which is double the normal bandwidth. And that's important because if you can't observe at 24 kilohertz and 37.5 kilohertz, you're missing some very useful frequencies. And I run Spectrum Lab. Now, I've never tried a Raspberry Pi. Now, I presume it's possible to do all this on a Raspberry Pi, but someone else can tell me that. So that would be an even cheaper way of getting started. And when you run Spectrum Lab, this is the sort of thing you get. And you get some very nice peaks, which have very good signal to noise. And as you can see here, you've got 6 peaks from the various transmitters. And the one at the end is the one at 24 kilohertz. Now, when I tried, as I say, when I tried this with a standard PC with only 24 kilohertz bandwidth, it cuts off before you get to 24 kilohertz. So it's important that you do have this wider bandwidth so you can see the NAA transmitter. Now, this is a very ancient version of Spectrum Lab. I'm running version 2.77. The latest is 2.95. So I don't know if they've changed the displays. The display might be slightly different from the latest one. But again, I work on the principle that if it works, why should I use a later version? And so that's what the waterfall display looks like. And you can specify a number of bands of frequencies to record on a chart. And what I do is I use 150 hertz frequency range. So what I do is I take the transmitter frequency and add 75 hertz and take off 75 hertz just to cover the modulation, because there are problems that they use frequency shift keying. They're sort of teleprinter style transmissions, but there's the Iceland station has a habit of putting on a test tone, a 50 hertz test tone. And I've been fooled because when they put the test tone on, the carrier level goes up and down, and that makes it looks as though the ionosphere is waving about, but it's not, it's the transmitter. That incidentally is another reason why you should observe on more than one frequency, because that helps you to remove the effects of any transmitter changes, like changes in power, modulation, that sort of thing. If you've got more than one frequency you're observing at the same time, and it only happens on one, then you begin to get a bit suspicious. And what I normally do is look on 9 frequencies at once. And this is the sort of chart you get. And I average it over a few seconds in order to reduce the noise over 5 seconds, or you can choose the amount of averaging you like. But obviously you don't want to go to too much an extreme, because you'll flatten out some of the sharp rises that happen. And the other thing I do is I use a linear scale. I know I've seen people run with a logarithmic scale, but the problem with that is that if you've got a high signal and a peak on top of that, using a logarithmic scale, it flattens the peak and it makes it less visible. So I always use linear scale. And you can see the amplitude varies for each of the transmitters. And just pointing out Anthorn and Skeleton, you can see that they're on all the time and everything's quite nice. But this one in yellow, the one in Germany, the Rauderfane transmitter, if you want to attack German submarines, do it for an hour from 7 in the morning, because the transmitter always switches off for an hour over that period. And again, this is why you should always monitor more than one frequency at once, because quite often the transmitters will go off for a few hours, a few days, a few weeks, or it may not come back for a few months. So if you observe 9 frequencies at once, you usually find one of them is off air at any one time. So yeah, you can attack Germany from 7 in the morning. And so what do we see? This is my carefully selected typical example of the sort of things that happen to the amplitude of the Anthorn transmitter during the day. And what you find is that the ionosphere is very unstable at night. Now, I keep reading different accounts as to what happens to the D layer at night. Some reports say it disappears completely. Others say it goes up to 90 kilometers. But to my mind, it appears and disappears all the time, because the only source of the ionization are things like cosmic rays, say particle input from the magnetosphere and all that sort of thing. You haven't got this steady extreme ultraviolet from the sun. And so what happens is it's totally unstable at night, and then at sunrise, the D layer forms and everything settles down. You get a nice steady signal strength from the sky wave. So that's at night, all this rubbish over here. Then it's nice and stable. Okay, it goes up and down, but that's okay. And then at sunset, you get the reverse. The D layer decays and the whole thing becomes unstable. Now, I am always very dubious when people say they've detected something at night, because in my experience, the amplitude goes all over the place in a random fashion. So even if you've got multiple frequencies, there's always a likelihood that some of the peaks will line up. So I'm always a bit dubious if people say, oh yeah, we saw something at night. So yeah, it's very stable during the day, and noon is about here. So most of our observations are during daytime. And this is my carefully selected typical example of a sudden ionospheric disturbance. And this is what we all want to see. Looking like this, you know, isn't all that unusual, but this is, you know, one of the best examples I've got. And what happens is you get this rapid rise to a peak, and then a slow decay down. And this is stuck on top of the normal amplitude change you get from sunrise over here to sunset over there. And Wikipedia, the fountain of all knowledge, says that the ionospheric disturbance, this thing, enhances VLF radio propagation. So you think, well, this is good. Yeah, I'll get more signal. It enhances VLF radio propagation. So it must be right. Until you look at skeleton, and that does exactly the opposite. They're mirror images. So where Anthorn goes down, skeleton goes up. Where the SID goes up, enhances propagation, skeleton goes down. And then at the end of the day, when Anthorn goes up, skeleton comes down again. And it was seeing this mirror image of the amplitude that caught my attention in the first place, and that got me interested in doing more things than just looking at SIDS. And one of the useful things, of course, is that it helps you to identify SIDS, because interference always goes up in amplitude. You never get interference decreasing the amplitude of what you can see. But with SIDS, they're always mirror images. So you might have noticed the two peaks over here, which is another SID. And this time, the skeleton one goes up in amplitude and the Anthorn goes low, but they're always opposite. And this is why you've got to live at the center of the universe. So here I am in Bingley Woods, center of the universe in England. And Anthorn is up here and skeleton there. And conveniently, they're quite close together. So it means that the path from here up to Skelton and Anthorn are more or less over the same route. And the reflection point, the midpoint, because I'm assuming here that we get one reflection off the ionosphere because they're so close. They sample the same region of the ionosphere. So anything that happens to the Skelton transmitter sky wave, you'd expect to happen to the Anthorn one as well. The only difference is on slightly different frequencies. And of course, the effects we're seeing here are to do with the interference between the ground wave that follows the curvature of the Earth and the sky wave, which bounces off the D layer of the ionosphere. And so I thought, well, as they always do the opposite, there must be some way of working out how high the ionosphere is. And what I've done here is to show the heights at which you would get constructive and destructive interference between the ground and the sky wave for the two frequencies. And if you just look at one frequency, you can't work out whether the maximum, say, comes from the ionosphere being at 29 kilometers, 53 or 69 or 83. But because the two transmitters always do the opposite, you can find a match in this region where these three peaks and troughs line up and they're opposite to each other. This is the minimum, that's the maximum, that's the maximum, minimum, minimum, maximum. So it helps you to resolve the confusion about which are the minima and maxima you're looking at. So what happens is at the start of the day, the ionosphere is very high. And then when the sun rises, the intensity of the ultraviolet increases as the sun comes up above the horizon. And that means that it ionizes low down in the ionosphere. And so you get this lowering from dawn to noon. And then if you have a SID, the increased radiation from the X-ray lowers the effective reflection height of the ionosphere further. So if you work in this region, then you find that Anthorn and Skelton will always be more or less lined up opposite each other. And that's what I did, to try and devise a model which would allow me to calculate how high the ionosphere was at any time. So if you go back to our charts, you can see that the peaks here are where the ground wave and sky wave are in phase, and the troughs are where they're out of phase. And when we get a lowering due to the X-rays, the X-ray flare, in this case, that moves an in-phase signal out of phase again, and the same goes here. And on the Anthorn side, it does the reverse. The lowering moves the two waves back in phase here and here. And if you look at all 8 frequencies, then this is an example of M2.4 solar flare created a SID on January. It's got 8 frequencies running, and what you find is that 4 frequencies go down and 4 frequencies go up, and that's solely because of the phasing effects of the different frequencies, the different distances of the transmitters, and so the different phase difference between the ground and the sky wave. And again, because you've got 8 frequencies on the go, you can tell the SID's in the middle, and all these other glitches that are due with changes of transmit power or the transmitter going on and off. So you can say, oh, they're not SIDs, that's a transmitter effect. And the other interesting thing is don't fall into the trap that the SIDs always go the same way with the same transmitter. This is on 18.3 kilohertz. One's on the 6th of January and one's on the 7th. And it just so happened the SIDs are on exactly the same time, but they go in opposite directions. And the reason for that is that the out of phase point is down here at the minimum. It went through the out of phase point, started to go back in phase, then the SID came, so it put it more in phase, so it went up. And on the other day, it was on its way down to out of phase, didn't manage to get there. The SID came, that lowered it to the out of phase point, and then it bounced through that, started to go in phase again. So when you look at this, it's not 2 SIDs, it's 1 SID, but it's gone through the out of phase point. So it's interesting that, as I say, you've got to get yourself familiar as to what normally happens when one of these flares comes along. Don't get fooled by this going through 0 phase point. And once you've done all this, you can record your observations. So what you do is you record the start time. Oh yes, I can find that. And the peak time, or the minimum, depending on the phasing, and the end time. And you can have hours of fun trying to find what the end time is, because the SID normally starts sharply and ends slowly, so it's always difficult to try and work out where the end time is. Once you've done all that, you send your observations to John Cook. That's his email address, jcook@jcookplus.com, and he coordinates all our observations, and every month he produces a report from them. So yeah, that's how you can recognize SIDs and report them. So what we've just seen is the process. So we have a solar flare that generates X-rays, that increases the D-layer ionization, that lowers the effective reflection height, and we get our SID. And what we actually see, of course, is the reverse. So we have to deduce that we see a SID, that means the ionosphere lowered itself. And that was because of the increased ionizations, and that came from the X-ray from the solar flare. Now, every talk has to have a bit of a mass in it. So I thought, oh, I will show you this equation. And this is showing you the production rate of ions in the atmosphere. And it's such a hideous equation, but luckily for us, what you find is that the reflection comes off the part of the ionosphere where there's maximum ionization, and the height at which there occurs is nice and simple. So I can get my head around this, rather this other equation, it's a bit hideous. Anyway, so this is our little equation, and this says that the height of the ionosphere depends on the height of the ionosphere when the sun's overhead. So the zenith angle is 0. So if the sun's directly overhead, the ionosphere is at its minimum, which is h0. And then as the sun rises, so this angle what is it, chi or whatever, as their angle increases, so this log goes negative, and so the height gradually increases. And the rate at which it increases depends on this scale height. And the scale height is just the height over which the density of the atmosphere lowers by 1/e. And it's got the usual things in it: Boltzmann's constant, the temperature of the layer, the mass of the ions, acceleration due to gravity. So I thought, oh, we've got a nice little equation. Does it describe what we actually see with this variation of amplitude of these VLF transmitters? So you can work out easily what the height of the sun is during the day, and it produces this nice curve doing the right thing, lower at noon, higher at sunrise and sunset. And then underneath is the predicted amplitude of 19.6 kilohertz. And you think, that looks very good. It's the right shape. And what you find is that you can fit one frequency with that curve. But as I said before, there's this anomaly that you can't work out definitively which height you're talking about, because the minima and maxima can occur at many heights. So what you do is you constrain the model by fitting the two frequencies at once, Anthorn and Skelton, and this is what you get. And you think, oh, that's pretty good fit. And from that, out of the model comes these figures for H0 and the scale height. And the interesting thing is that if you take the figure for the scale height and you assume the temperature of the D layer is about -40 centigrade, and I struggled really hard to find a definitive figure for this. So if anyone knows what the real temperature of the D layer is, I'd be interested to know. But anyway, if you plug that in, then you can find the mass of the ions that are being ionized, the atoms are being ionized, and that comes out to just over 30 mass units. And satisfyingly, the main ion is nitric oxide, and that's got a mass of 30 mass units. So, we're in the right ballpark here. So you come out with a reasonable result. So I felt that was quite satisfying. From this very simple model of just a single reflection, you can get that sort of result. Oh, and I fitted it using a steepest descent algorithm. It's one I use since my student days, but mass doesn't have a sell-by date, so I'm still using it. It works. So I thought it was interesting because this from 1950 indicator was installed in the solar department at Herstmonceux. This radio equipment in recording the combined amplitude of the ground and sky waves radiated by GBR rugby on a wavelength of 19K registers the occurrence of sudden changes of phase difference due to the effect of solar flares on the ionosphere at about the 70 kilometer level. And I thought it's interesting, they were called SPAs in those days, not SIDS. I thought it's interesting because where I live, I'm less than a wavelength away from rugby radio, which doesn't exist any longer. It's a housing estate, but yeah, I thought I'm less than a wavelength from that. Yeah, so observations of SIDS have been going on since at least 1950. And you might be saying, well, I don't think your fit's very good, but you can get a better fit if you combine a single reflection of the ionosphere with two reflections, and that fits really well. And of course, if you added more reflections, or if you could get your head around the mathematics of waveguide modes, you would get an even better fit. But who was it who said, keep it simple, stupid? And that's what I've done. Anyway, another thing you can get out of this is the amplitude of the ground wave and the sky wave. And I thought it's interesting because what I show here in blue is the ground wave at 22.1 kilohertz, so that's skeleton, that's the closer one. And then the yellow is the ground wave at 19.6, and this is from January to September. So the heights tend to be a bit erratic in the winter, so I wouldn't take these as absolute points. You know, they need huge error bars on them, but you can tell that it's more or less constant throughout the year. And the same for Anthorn's ground wave, but there's a definite reduction in the sky wave as you go from winter into summer. And I'm not too certain of why this is, because I've read several things which conflict with each other. So again, I'd be interested to know what the definitive answer is. I noticed that the ITU produce curves and graphs for you to be able to calculate what the expected amplitude of a medium frequency radio signal should be. And they say that the sky wave decreases during summer as opposed to winter as well. Now, whether this is to do with the ionization being lower, and so you've got more absorption on the sky wave, I'm not sure, but it's an interesting effect you can get out of just this simple model fitting. And if you don't believe me that it is reduced, I thought I'd show this curve. This shows you the seasonal change on 19.6 kilohertz. So in blue is 21st December, midwinter. And you can see during the day when the sunrise bit is over, you've got a huge difference between the maximum and minimum. So between the in-phase and out-of-phase point, there's a huge difference. So showing you there's a large input from the sky wave, whereas the pink curve is for midsummer, and the peak over here isn't very high above the minimum. So it's a definite effect. So I'll be interested to see what people's thoughts on that is. Yeah, I know it used to be said that you can't see SIDS using Anthorn and skeleton because they're too close. The ground wave dominates. Well, as we've seen, that's not the case at all. The ground wave is generally higher, but the sky wave is still there, a significant percentage of the ground wave. So yeah, don't give up on Anthorn and skeleton. And of course, you can do this throughout the year and produce a nice little graph that shows you how the height at noon, that's the minimum height, varies throughout the year, and fit another curve to it. So again, you can see the height at the summer solstice is the minimum as the radiation gets down lower, and it's highest in the winter. So you can fit it for 1 year, and then you then can look at how it varies from year to year. So this starts in 2010, goes through the complete sunspot cycle up to the present day. And the minimum height, that's the height in June, is about the same, and there is a gradual rise up. So whether that's real effects, I don't know, but I thought that was interesting that since 2010 it has gradually risen up. But the maximum goes up and down a bit. Now, you can try and associate that with the state of the sunspot cycle. But the problem is fitting the maximum relies on the height of the ionosphere in winter, and it does vary dramatically from one day to the next. So I suspect this is probably a model fitting problem and not a real effect. But anyway, there's a little dip in 2011 and a little dip at 2015. So if we look at our plot of the number of SIDS throughout the year, which is in blue, and the number of sunspots, which is in yellow, 2011 is round about the first peak on the sunspots, but 2015 is after the peak of the sunspots. So, you know, I'm a bit dubious as to whether that's a real effect. But what is real is this periodic nature of the blue line. And what you find is that about every dot is a month. So about every 4 to 5 months, the number of SIDS shoots up and then drops down to really low level, which seems to be independent of the sunspot numbers, which are in yellow. And other people have noticed this, and again, I don't think there's a concrete theory as to why that is. I mean, obviously, because we've got a periodic number of SIDS, that means there was a periodic number of solar flares. And with the SIDS, you tend to only notice flares which are stronger than about B5 or mainly C-class flares. So this only counts the stronger flares. But even so, people have tried to work out what's going on in the interior of the sun with the solar dynamo to try and work out why it should be that you get this periodic nature of these most powerful solar flares. It's not as though it's the same sunspot coming round, because that's only a month. This is after 4 or 5 months. So that's another interesting thing you can get from just doing simple SID counts. Another thing intrigued me is, why are SIDS sudden? You know, sudden ionospheric disturbance. And the simple reason for this is that the ionization just follows the changes in the X-ray flux. So in green, this is the X-ray flux from the sun. And what you find is every peak follows what the X-rays did. So when the X-rays shoot up sharply and decay slowly, that's what the VLF amplitude does. And then there's one over here where the rise is a bit slower, and sure enough, the amplitude rise is a bit slower. But the interesting thing with this day, each of these peaks and troughs is due to a solar flare, is that you can work out what height the ionosphere was where these X-ray flares occurred, and you can plot them out. And you can get a nice, more or less straight line relationship. And what I'm plotting here is the height of the ionosphere versus the log of the X-ray flux times the cos of the solar zenith angle. So in effect, this is just taking the log of the X-ray flux and saying, well, taking into account the height of the sun, that's directly proportional to the height of the ionosphere. So you can work backwards, which is what I was saying with the deduction, that from knowing you've got a SID, you can work out what the height is, and from the height, using this sort of relationship, you can find out how strong the X-rays were that produced it. And this is another beautiful example we had of how the amplitude directly follows the X-ray flux. Because believe it or not, all these little wiggles and humps were produced by the X-rays. So we had sort of pulses of X-rays which grew and grew and grew. And sure enough, the amplitude at each of these, 4 frequencies directly followed the X-ray changes. So that was a superb example that when you have these stronger X-ray flares, that the ionosphere just follows blindly on from what the X-rays are doing. So that was SIDS produced by X-rays, but you find there are some effects which look like X-ray SIDS. But when you look at the X-ray flux, it's not doing anything particular. What I found is that this effect tends to only happen on the path to Iceland. And this was an example from last month. So what you find is you can't see any relationship to X-ray flares, but if you look at the Mall magnetometer, and I draw in a line where these rapid changes are on the magnetic field of the Earth, you find the peaks match those sharp changes. And this isn't one example. I've seen many, many examples of this. So what this is charged particles coming down onto the ionosphere and increasing the ionization. Now, the thing is another sheer fluke is that the path from central universe here up to Iceland happens to go directly by Mull, where the magnetometer is. So the path, the ionosphere, which is suffering this particle input, is also going through the auroral halo, which sort of goes around near Iceland. So you've got these two nice effects that you're sampling all these particles coming in down the Earth's magnetic poles, and at the same time you've got, presumably, they're jiggling the Earth's magnetic field around and being picked up by the magnetometer. And I don't see those, even though Anthorn and Skelton are more or less in the same direction. You never see it with them at all, except if you get a big particle input from a CME, a coronal mass ejection. If it's just your sort of bog standard fluctuations in the solar wind given this particle input, you don't see it on Anthorn and Skelton. But if it's a more powerful input of particles, which gets down to lower levels and lower latitudes, that's what I was thinking of, you get this sort of thing. And what I'm showing here is in yellow is September the 12th, and in pink is September the 11th. So you've got a baseline to compare it with. And so you get this SID, and that's produced by a coronal mass ejection. But the interesting thing with it is you get the coronal mass ejection, and then you get this wiggle on the end. And remember I said it's important to have two transmitters. You find you've got the same wiggle on skeleton as well. So you think, oh, this is a true effect. And what this seems to be is what's called a gravity wave induced large scale traveling ionospheric disturbance. Now, this is a gravity wave. It's not a gravitational wave. This is a gravity wave, which is a displacement wave. And from what I read, what seems to happen is the particle input heats the atmosphere up, and that moves obviously it moves the gas because the expansion, and that expansion produces a wave in the ionization on the ionosphere. So yeah, these are TIDs. Apparently there are medium scale ones as well, and even smaller ones. And this was another example. This was on March 9th, 2012. And this was the day where there was a magnetic storm. I think there was a magnetic storm the day before as well. And what I'm showing here is the top line is the signal from the German transmitter, and the bottom two are Anthorn and Skeleton again. So these are to the north of me, and the German one is to the east. And what you see is this wiggle is the same on each transmitter, except that there's a 32-minute delay between the pass to Germany and the pass to the north of England. So you think, well, this looks like it was a wave of ionization, a TID, a traveling ionospheric disturbance. And if you look at the difference between the midpoints, the reflection points between going up to Anthorn and Skeleton and going across to Germany, you can work out the speed, and you get 715 kilometers an hour. So that's about half the speed of sound. So it's a very fast moving wave through the ionosphere, which I thought was very interesting. And you can get even more extreme examples. I've yet to see a proper explanation as to what causes this, but sometimes you get these very rapid oscillations, and they always tend to be about 5 minutes. And you see at 3 frequencies, so you know it's a real effect. Now, whether this is due to, as I was saying, what's it called, the jet stream, turbulence in the jet stream wobbling the atmosphere, because from what I read, this particle input, which produces the heating, and the gravity waves it produces, they're always of long wavelength, about 1,000 kilometers, and they're slow moving. So the periods is only between about 30 minutes and an hour, but these are much more rapid every 5 minutes. So I say I haven't found what the source of these are. So that's and also they tend to only be seen on the northerly path, or this path to the east. I never see them on the path to America or anything like that. And people have measured these TIDs using rays of GPS receivers. So they sort of cover the whole of Europe with GPS receivers, measure the slight time differences on each one, and you can plot the total electron content. And the red areas are where there's more electrons than others. And you can see they appear in bands, and these bands actually travel southwards, so that when they go over the reflection points, they wobble the ionosphere up and down, and that's where you get the waves and the received amplitude. And what intrigues me is noctilucent clouds. Now these up at 80 kilometers, so they're just above the D layer of the ionosphere. And you can see, this is a picture I took a few years back, you can see this sort of wave-like structure. And you can imagine if these waves are traveling overhead, that might give the wobbles that I was seeing. There's only one problem, you can only see these at night, and I can only do my observations during the day. So I can never see the two at the same time to see if when I get these very rapid oscillations, whether they're the same ones as in these noctilucent clouds. So I've talked at great length about all this ionization which is produced in the ionosphere, but there are occasions where something comes along and takes the ionization away. And one example of that was when we had the total eclipse in 2015, and the path went across Spitsbergen, but down in Europe, we had about 80% covered. So we had a really deep eclipse. I didn't go to Spitsbergen, Mike Frost did, but I didn't. That was the picture of the optical eclipse. And this was my picture of the radio eclipse. And the top trace comes from, that's the eastern passage of Germany. And the bottom one is the skeleton. And you can see both have a dip caused when the sun was obscured. And I put a line in to show you where the maximum eclipse was at the reflection point. And what you notice is that the dip, there's the maximum eclipse occurred in England before it occurred in Germany. So there is a slight delay as Raudefen is further east. But having said that, there was a delay between the optical eclipse and the radio eclipse of 6 minutes. Now, I didn't imagine this because other people have seen this as well. And from what I understand, although I'm still a bit confused, is that this is to do with the relaxation time it takes, that when you take the ionization away, it takes the ionosphere a few minutes to sort itself out. And of course, you can fit a model to this, which fitted quite well, even a little wiggle at the end. And you can produce a little picture which shows you what the height of the D layer did, gradually reduced during the day and then shot back up again by about 8 kilometers during the eclipse. That's the maximum eclipse in the middle. This isn't new either, because I found this one from trouble is I can't see the top of my screen. It tells you what date it is a long time ago anyway. But the interesting thing is it says that under the direction of Dr. Van der Pol, in collaboration with Professor Appleton, Wheatstone Professor of Physics at the University of London, the famous Dutch wireless station at Eindhoven will send out a steady Morse dash from 4:30 to 8:30, that's a long dash, on Tuesday, Wednesday and Thursday morning on a wavelength of 30.2 meters to enable experimenters to note the effects of the eclipse of the sun on the strength of wireless signals. I presume the signal increased because the absorption and the delay would have gone. And we can try this again because there's a partial eclipse on the 10th of June. This one isn't as deep as the last one, but at least it will be interesting to see what happens. I'm getting very thirsty, so I'm going to finish with this last bit in the end, and that is other sources of interesting things which can happen. I mentioned gamma rays. Well, gamma ray bursts have been detected. Well, I say detected on VLF, but I'm a bit dubious with this. I've no this. I'm not trying to cast aspersions on on the Indian observers, but I've read papers before from there, and some of the things aren't quite right. So I have my doubts, and it was done at night as well. But this shows you the gamma ray count with the burst that increased, and then the other three traces are VLF signals to three different transmitters, and they all have the same sort of shape. And I say that concerns me. If I'd have seen some go in the opposite direction, and these are in dBs as well, I might have believed it more, but they claim to have seen a gamma ray burst. So that's one thing you can look at for. Magnetar soft gamma repeaters were detected in Brazil, and at the bottom is the count, which shot up, and then you've got the amplitude. This time it dipped, and the phase, which wobbles about. And this is the path from Brazil to Hawaii. And again, I was surprised that the amplitude went down rather than up. So again, I'm a bit dubious about that, but they claim to have seen a magnetar. Bolides, when we had the Chelyabinsk meteor, there was a TID setup, which was detected, and these show the fluctuations in the total electron content again. And these were near where the meteor came down. I looked to see if anything had propagated our way, but I couldn't see anything. And apparently this was not so much to do with the increased ionization, but to do with the shock wave, which sent a TID through the ionosphere. Nuclear explosions, luckily, it's not the 60s, but North Korea has this habit of blowing one up occasionally. And again, that seemed to have created a TID, which was detected in South Korea. And this time it was more to do with the infrasound, the acoustic shock affecting the ionosphere. And earthquakes, the enormous Japanese earthquake, the tsunami from it created a gravity wave. You know, I mentioned about sea wobbling, and these plots show again these waves in the total electron content caused from the earthquake. Interestingly, if you've seen the recent volcano in Iceland, that's only a few kilometers from the VLF transmitter there, and they had 30,000 earthquakes in a month, or was it a week, a couple of weeks back before the volcano went off. And you know what effect it had at 37.5 kilohertz? None at all. So I was very disappointed with that. And finally, supernovae. We're still waiting. I was thinking, oh great, Betelgeuse is going to blow up, but unfortunately it didn't. But we did have one in the LMC in 1987, and I've read theoretical papers that said it should have been detectable, but I don't think anyone was observing in the right mode at the time. So I haven't seen that anybody actually saw it, which was a bit of a disappointment. But we're still waiting for a supernova. With that, I'm dried up, so I'm going to finish with this picture of the aurora, which I thought was quite pretty. That's it. Thank you very much. How do I stop?
At the top of your screen.
I do that. Yeah, I'm back. I'm back.
Okay. Thank you very much, Mark. That was a real inspiration. Many of us are SID observers, and I think you've given us there a huge amount to think about. Before we move on, let's just take some questions. If anybody has a question, then
Don't guarantee to answer.
Then please ask. Yes.
And Andrew put his hand up, but
I kind of waving. Mark, you talk about reflection from the ionosphere and modeled two different frequencies
yeah.
and got different degrees of fit. Would there be inherently, because they're at different frequencies, would the reflection point or the refraction path through the ionosphere be different at two different frequencies?
Yeah, I mean, they're at slightly different distances as well. Yeah, I mean, it's a very simplified view because in practice, it's not a sharp reflection. It's more of a gradual refraction through the ionosphere. So yeah, different frequencies obviously would refract by a different amount. But I mean, they're so similar in frequency, I would suspect it's not very much at all. I mean, the absorption is different to different frequencies as well, which is another thing to take into account. And as I was saying, if you do the proper equations, like the sort of waveguide propagation equations, that a double reflection goes into the ionosphere to different angles. So the absorption and refraction is going to be different. So it gets hideously complicated. And that's why I only took this simple approach, that I'll just use straight lines, flat surface, away you go. But yeah, I agree. It would do all those sorts of things. Any more for any more? They've all fallen asleep.
There were some questions on the chat stream as well.
Oh, Jose.
Yes, I did. I was about to say that Martin asked the question regarding to the screen on the SCART lead, whether or not that would desensitize the aerial's usability.
Well, yeah, I connect the screen. I know people say, oh, the screen doesn't do anything. But the crucial thing is you don't join it in the middle, otherwise you short the loop out. So I connect the screen to Earth at one end and leave the other end open. And the other thing I forgot to say is it's not tuned at all. Obviously, you've got capacitance there, natural capacitance, so it will resonate at some frequency, but I never bothered. You don't tune it, because obviously if you tune it too much, you don't see a large band of frequencies. But I would think the screen, it stops the sort of capacitive coupling of interference sources nearby. The other interesting with the loop is you might have noticed there's a radio in the middle, and that's my digital radio. And I switch that on and I don't have any problems with interference. The main interference source of the old compact fluorescent lights, the switch mode power supply in those is absolutely awful at 37.5 kilohertz. But it sits in the same room as my PC and all sorts of other things, and I don't have problems at all with it. But yeah, don't attach the screen, but don't attach the other end. So someone just then said he stopped looking at solar minimum. Yeah, I mean, as I was saying, I think it's important to look at solar minimum, because even though we haven't had the X-ray flares, we have had these sort of particle inputs from shocks in the solar wind, CMEs and that sort of thing. And as I was saying, it's important to look at solar minimum because you work out what the normal is. So when something starts to happen on the sun, you'll know that it's abnormal and you'll take note of it. Howard's waving is. Paul, did you see Howard?
Sorry, say again.
Howard was waving his. Oh, I think he's disappeared.
Are there any other questions? If not, we'll move on. Mark, thank you so much. That was a great inspiration and filled in lots of gaps in my knowledge and probably others as well. Would you be prepared to send a PDF of your presentation to those that want to go over some of your charts again at their leisure?
Yeah, if you want, yeah.
Okay, can I suggest, rather than just put it on a public space, if anybody would like a copy of Mark's presentation, to send me an email and I'll forward it on to Mark and he can share his data. Thanks very much, Mark. That was greatly appreciated.
Yeah, that reminds me, all of my raw data is in the SID archive that I can't remember who set it up, but he asked all the observers to send him a copy of our raw data. So somewhere there's an archive of it all.
Interesting. Does anybody know who manages that archive and how we can get access?
It was a project started by Andrew Lutley, and I know he's recently revived his interest in it. He's been talking to people and putting data in it, and I think his ambition now is to make it a bit more user friendly and find a way of getting data out of it.
Watch this space, I say. Watch this space. Okay, thank you very much. I guess if we were in a real meeting, then we would give you a round of applause, although that's not so easy.
Thank you.
But you get the idea, I'm sure. Right, I'm going to save the breakout room option for another occasion, so something to look forward to there. I'm going to move on to Andrew Thomas. I believe you have something to share with us, and embedded in your comments may be an advert. Is that correct?
Yeah, sort of. We'll go get round. I put my cards on the table. I'm a director, board trustee of UCRA, and I'll talk about briefly some of the equipment we make for observing SIDS. So if I just work out now how to share my screen. Can somebody remind me how to share my screen? Ah, there it is.
The green.
Share.
Yeah, that worked.
That's disconcerting. I have now completely lost my view of Zoom. Never mind. I have a very short presentation, and I just want to say that everything I'm saying in here is entirely personal, apart from a short advert at the end. I started observing SIDS about 3 years ago, so I've had the pleasure of watching solar minimum, but can't say it's entirely boring because things do happen, as Mark has kindly pointed out, and that I take his point that it's very useful to watch when nothing's happening, so when you do see something happening, you spot it. I just want to say how I got started, the equipment, a little bit about equipment, the science, a little bit about interference, because I think that's a topic that Mark touched on, and just ask people whether they're interested in putting their observations live online in real time. So now Mark's preempted me. John Cook, director of the radio section, has been running a collation of SIDS observations for many years now. I'm not quite sure how far this goes back, but it looks like sort of 15 or 20 years. And that produces some interesting statistics. And when I was had discovered radio astronomy and was looking for a starting point, somewhere I could start with almost no practical electronic or technical knowledge, SIDS seemed to be something that you could do with you could buy something to do the receiving, which is my chosen route. It's a different way of doing things to the one Mark's described. I saw that you could build the aerials for it without an awful lot of sheer size, I think, if you look at some sort of low frequency antennas. So I leapt in, and I liked the idea that there was some science and some observing behind it. It's a little bit like doing the sunspot count if you're a visual observer. That quite appealed to me. So I set to, and I built myself one VLF receiving array using the UCRA receivers. I built an antenna. If you look at the bottom there, the one on the far wall is an east-west antenna, some leftover roofing battens, a little drum of enameled copper wire, 100 turns of wire, and I've got a very, very functional aerial. So after about 12 months, I thought, might be interesting. Let's have another one. So I built a bigger aerial to see if it was feasible and possible to build a bigger aerial. And the answer I got was, yes, it's feasible. Yes, you can do it. It probably isn't really worth it because I'm not sure it performs any better than the slightly smaller one. And if you look at the aerial UCRA produces, that's only 400 millimeters on a side, and it's a little thing that can literally sit on your windowsill. So for the UCRA designed receiver, which is a single channel device, it's important to tune the aerial because it needs all the help it can get to get as much signal into the receiver. The receiver turns out DC, so you can turn that into a digital value, plug it in with a bit of an A to D converter into your PC, some free radio SkyPipe software, and you're in business, you're observing. Compared with what I think you could spend on camera equipment for an optical telescope, a fairly low cost leap into a new hobby. I quite enjoyed this, and I was just getting a few results. I'd seen some SIDS. And in the last sort of 12 months during lockdown and last summer, I took all my equipment, moved it out of the house and moved it into the shed. I guess domestically, it was a good arrangement, and added a magnetometer, which took a bit of setting up and finding a good place for it. I'm still putting effort into sort of finding a best way to mount it and keep it stable and that sort of thing. And it's absolutely fascinating results. I also moved over to using a Raspberry Pi instead of a PC. Again, after a to D converter. And now I'm logging and analyzing my data using some homebrew Python, which is the other thing I've found with this as a hobby. It's a great way to give yourself a project and learn things you might have wanted to have a dabble at, and suddenly you've got a reason to do it. Coming to reasons, the reason for moving from the house to the shed is the installation of solar panels. Now, Mark's mentioned his bête noire of noise, which is lousy power supplies in low energy fluorescence. What prompted my shift was solar panels. Now, it was pretty obvious that it was the solar panels, because sort of the day before they were turned on, I didn't have noise like this. And the day after they were turned on, there it was. And a couple of hours work on a week's worth of data. Sunrise is just about there and sunset is just about there. And that's the point where the solar panel controllers start shutting them down, because there's not enough photons to make worthwhile electricity. So these spikes, this fuzzy noise all through the day, it was the solar panels. Moving 120 foot down the garden has got rid of the problem almost completely. So as you can see there on a trace for the 29th of May last year, couple of nice SIDS and my interference. Now, I dealt with the interference, and it's a subject I'll return to in a minute, because it's not just a problem I've had, and it's sometimes very difficult to find out what it is and eliminate it. So Mark has talked about propagation, so I thought I would take a cue and put up a slide showing some odd propagation effects, and I'll be interested in Mark's comments perhaps and other observers. What you're looking at here is I had a receiver on test on 23.4 kilohertz, and there's the blips at fairly regular intervals. Now, my first reaction was, I've just made the receiver, it's under test, there's something wrong with the receiver. I haven't built it properly. I haven't tuned it properly. So I downloaded Monsieur Laudet's graph, and he actually lets you download his data. So I've replotted the graph. It's a bit more difficult to see, but on his trace, these blips here coincide spot on in time with the blips I was seeing. So my conclusion was, this is a real effect. What it's a real effect of, I have absolutely no idea. But I've noticed these things happening before, and I think this is building on Mark's comment. Observe at solar minimum when nothing much is happening, and you start seeing all sorts of strange events. I'm working with one of our UCRA customers who's having a problem with interference. And when I saw these blips, for want of a better word, he'd been sending me traces of his interference. So having put my receiver on test, the German military shut their transmitter down, which is a bit of a pain, but it does actually let me show you what a receiver should be receiving when there's no signal. And the answer is it receives nothing apart from a tiny little blip of local interference. But our customers' trace for the same day, same period, is showing quite significant blocks of interference with a background level of interference and points where it goes off. Now, as we discussed this, our first thought was it's a fridge, or it's several fridges. But so far, this has completely eluded the interference hunter. And I'd be interested in other observers if they would like to say what their favorite or most unfavorite form of interference is, and what sort of devices they've managed to track down interference to. Because at the moment, both of us are looking at this as somewhat the blind leading the blind. Neither of us have got a clue what it might be. So they're the things I wanted to say. Now the online bit, if I can find the controls, I wanted to show you a screenshot of my online real-time plotting, but Zoom seems to have so completely hidden.
You might need to unshare and then reshare the other monitor.
Ah, okay. That might be the quickest way of doing it. You're right. Right, you should now see my screen of Firefox. And if I refresh it, you should now see my screen of Firefox up to date. 2055 local time, yes. What I've been able to do with my homebrewed bit of Python, and I know that Radio SkyPipe can do the same thing, I throw up graphs in live real time onto the internet so I can, just see what's going on. And it's been really useful looking at Monsieur Laudet's site. Now, I haven't been able to find many people who've been putting their data up on the internet in realish time for sharing. So I'd like to ask people who have an inclination. It's not difficult. Have a go, and then it's useful for people who are suffering from interference or wondering whether something they've seen is real or their imagination, to have something to compare to, which is, screen sharing is paused. Stop sharing. Right, I'll stop sharing, which is, I think, something useful for observers to share their work with people. So that's just my ask for people to have a little dabble with the online world and see what happens. I'm now going to try and share. Lord knows. My last slide, which is just a little description of Eucra selling assembled boards, kits, aerials, and all the things to allow somebody with little experience of electronics to get started in observing SIDS. And that's all I really wanted to say. So thank you very much for your patience. And if anyone fancies asking my vague questions, I would be delighted.
Are there any questions for Andrew?
Oh, any answers?
Questions. Mark?
Yeah, first of all, on 23.4 kilohertz, what I notice is that the signal level jumps like that all over the place when nothing else does. So I've always put it down to a transmitter change. I haven't looked. Have you looked in detail at the modulation?
No.
On it, but I say I tend to steer away from the German transmitter because its transmitter level does jump about, glitches all over the place. So what you showed looks what it normally does.
Okay, that's interesting. Thank you.
Yeah, could I? As I say, I'm trying not to tread on people's toes here, but what I would suggest is that because PC sound cards are sort of limited in bandwidth, it might be useful to use Spectrum Lab up to 48K and then use your receivers beyond that, like 60 kilohertz MSF or higher frequencies. And so you've got a coverage of the sort of extreme VLF and going up to MF, which might be interesting that people could do, because I mean, everybody's got probably got a PC and they can just use the microphone inputs and a simple loop aerial to do the lower frequencies, and then use your equipment to do the higher frequencies.
There are many ways of doing it, and I think you could probably do the same thing on a Raspberry Pi with what's the thing called, GNU RF, or GNU SCR.
Yeah. I always live in fear of people putting solar panels in. Well, Warwickshire Council put a leaflet round trying to persuade people to install them recently. So, the other thing is that the one useful site, which seems to have disappeared, is the Keel long wave monitor. That was superb, but a couple of months ago it went off there, and I haven't seen it come back. So that was a real loss to us all.
Yes, I agree with that. I always found that very, very useful. The archive function there was astonishing.
Hmm.
Any more questions? Any more answers?
Yeah, I've got a quick one. It's really to Mark and Andrew, really. The use of a sound card for SID monitoring. Have you found the results better from the sound card perspective rather than, say, the Max 186 chip that you can build an analog to digital converter? Have you tried those and a comparison?
I had one on a board, but I've never tried using it to receive VLF. I mean, yeah, if it's standard analog to digital converter, I don't see why you shouldn't use that.
I've tried both, but I mean, the problem is now, of course, parallel ports are disappearing.
Just to pick up on the same question, I'd say that they're two totally different ways of achieving the same end. If you're going to turn something into a digital signal from analog, you need something to have done the tuning onto a particular frequency. I think the way of doing it with sound card, I've messed about. I will quote, messed about with it. I've hooked one of our aerials up to a sound card just to see what would happen, and it gives me a trace, and it gives me a lot of noise. So when I've tried to do it, yeah, I've used it for a quick check to see what's on air, which it really does. That works a treat. What I've struggled with is the complexity of Spectrum Lab to try and process out. I can make graphs of a day's results, but then trying to get those to look neat and tidy and do some averaging on them, I've found the scripting and interface of Spectrum Lab too complicated to get to grips with, to be honest. It probably needs more effort than I've given it to date.
I personally just followed the guidelines on Jim Sky's website, Radio SkyPipe, and there's some instructions there how to build quite a simple circuit. In fact, I think I obtained the chips through a sort of a sample basis that they sent me. There's different categories from A to D, and the A are more accurate. But I think I got them for free just as commercial samples. But the problem I find is with that method, as opposed to the sound card, is that if you don't, like you say, get it tuned right, once you hit the ceiling, is it 4095 millivolts or something, it just bottoms out, and then you everything gets completely screwed up like. But no, I was just curious because the computer, the tower systems I've got now are quite old, and I don't find it practical to use a laptop to conduct long period experiments. But,
that was the point where I threw a hissy fit, was propensity of any PC attached to the internet to demand constant updates at inconvenient times.
Oh, That's my PC runs XP still, so that's the advantage. It won't upgrade itself.
If it's not
Yes.
broke.
Yes, because I like to throw results up onto the internet. Of course, I can't. The option of running a PC without an internet connection kind of disappeared.
How do you upload your graphs? I used to do it with meteor detection, and I used, I think, some software called GoodSync. I think you have to pay for that. There might be alternatives now.
I do it by I started off running a website for a conservation group I was a member of, then ended up with a website on my own domain name. So what I've got is a bit of Python running that grabs the data, plots the graph, and then saves them as PNG files, so a graphic file, which are quite small. And then its final act is to use FTP to pop them up onto the appropriate directory of a website. So as soon as somebody calls it up pops the latest graph. It was one of those things. I thought this is going to be complicated, and it turned out to be remarkably straightforward. And it's also it's a function built in to Radio SkyPipe. It has some coding built in there to do that. You just need something on the web to display it as a web page. And I got a sneaking feeling Spectrum Lab has something built into it. It seems to have most things built into it except a tease made.
Yeah, I mean, on Spectrum Lab, I don't run any special scripts at all. All I did was play around with the menus he's already got, you know, for setting up things like the sample rates, the averaging, and the only other thing is that I export the data as a text file every day, and then throw it into Excel to produce the graphs.
Any more questions or comments out there?
I was just about to say we need something like a Raspberry Pi expert so that we can get this rolling, and using something as inexpensive as a Raspberry Pi, particularly now they've brought out, well, it's not the Pico because that's a microcontroller, but like the smaller version, which is about a tenner, isn't it? The Zero, I think it's called. But yeah, it'd be nice to. Well, I'm looking forward to sort of hearing about Python and radio astronomy. That'll be a good talk, I think.
Yes, the one thing that prompted me to move it to a Raspberry Pi was that the idea of putting a laptop in the shed really didn't appeal.
Will it run Spectrum Lab Raspberry Pi?
No,
Probably not Spectrum Lab, but there are quite a few radio astronomy projects that people have devised on GitHub. I think you need a fair command of Python to sort of utilize them and set them up. It's something that's a little bit above my station at the moment, but I'm working on it. It's just be nice if somebody sort of have something that was just like an MSI installer and it just works. But it's not that easy.
No, it sort of takes the fun out of it. But that's where what we sell from Buchra is that by using a commercial A to D converter, that the manufacturer of that supplies enough drivers and code to load onto a Raspberry Pi to allow you to interrogate the A to D converter without worrying about all the timing and addressing and code. Everything is taken care of. All you have to say is read me, and then do something with the answer when it comes back as a number of between 0 and 5 volts. So we've done, somebody else has done the really hard work.
Is there any need to the lab jack unit that you use or sell or whatever? There's a HV version. What's the benefits of that version as opposed to the less specified version as it is?
It's actually the bottom of the range version.
Right.
The HV bit is that there's 4 inputs on it which do 0 to 10 volts, which I think just gives people a little bit of flexibility. One of the outputs of our receiver is 0 to 5 volts. So you can select 0 to 5 volts or 0 to 2.5 volts. So if you've got only got 0 to sort of 3.3 volts and you selected the wrong voltage, we're kind of trying to make it sort of foolproof. So far, we've had no complaints that anyone's blown one up. It's also got all the usual things you'd expect of over voltage protection and reverse polarity protection. Now we're very much focused on making it as easy for people without a lot of knowledge. And that's why I so much enjoyed Mark's paper tonight. It's the science behind it is fascinating.
It's amazing.
It was me that had those funny traces, and I'm very new to this, and it's been a very steep learning curve. But I'd particularly like to thank both Andrew Thomas and Andrew Lutley for giving me so much help in setting up my system. So if you want a nuclear version, I would suggest go for it because they're very helpful in helping you set things up.
I blush.
That looks like a very positive note on which to conclude this evening. Thank you very much, Andrew. Just one point of housekeeping. There are quite a few useful comments and questions in the chat, and the chat file can be saved by clicking on the little 4 dots at the bottom of the chat screen, and then just clicking Save Chat. And Zoom will put that in your, I think it's either in the download or in a directory that it creates called Zoom in Documents if you're working in Windows. I think that's the way it works. It's not that difficult to find. I had a look after the last meeting. Thank you everybody for your contributions and participation in the questioning at the end, and we'll meet again in 2 weeks' time, where we have Witham Reeve will be addressing us from the other side of the Atlantic. So good night everybody, and see you again soon. Bye bye.
Thanks, Paul.
Bye.